We're going to show you some extraordinary images of space. And to do them justice, really, you need to see them across 400 ultra-high-definition television screens. The James Webb Space Telescope spotted it just outside of our solar system. At last, after years of anticipation, the James Webb Space Telescope, JWST, has peered deeper into the universe than any human-made device before it, reaching the very edge of the observable cosmos. In a moment that sent ripples through the scientific community, the telescope captured light from galaxies formed just a few 100 million years after the Big Bang. Structures so distant and so ancient that their photons have been traveling across the fabric of space-time for over 13.5 billion years. This is not merely another scientific milestone. It is a direct window into a time when the universe was still in its infancy, shrouded in primordial gas, and unfolding in a delicate cosmic ballet. What the JWST found at this boundary of the observable universe challenges long-standing theories, reshapes cosmological timelines, and propels humanity into a new era of discovery. Before we start, please like and subscribe for more updates. The James Webb Space Telescope was built for moments like this. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet wavelengths, JWST was designed to see the infrared glow of the earliest stars and galaxies. As light from distant objects travels through expanding space, it becomes redshifted, stretched to longer wavelengths. By the time light from the edge of the observable universe reaches us, it sits firmly in the infrared spectrum, perfectly tailored for JWST's advanced instruments. What it discovered in its latest observations is not just a faint speck, not just an elusive smudge on the edge of detectability, but whole galaxies, massive complex systems that formed incredibly early in the cosmic timeline. These ancient galaxies appeared far more evolved than theory predicted, with organized structures and star populations that defy our expectations of such a young universe. The light that the JWST detected originated from a time less than 300 million years after the Big Bang. That may sound like a long time, but in cosmic terms, it's the blink of an eye. Cosmologists once believed that the first galaxies wouldn't have formed until at least 400 to 500 million years after the Big Bang, and that they would be chaotic, lumpy, and mostly made of hydrogen and helium. Instead, what JWST found were galaxies that seemed shockingly mature, with defined shapes, large masses, and surprisingly high levels of star formation. Some even appeared to contain heavier elements, those forged in the hearts of stars and spread by supernovae, hinting that not only had stars formed, but they had lived and died quickly, enriching the universe much sooner than previously believed. The implications of these findings are staggering. The presence of complex galactic structures so soon after the dawn of time suggests that the process of cosmic evolution happened at a much faster pace than previously assumed. It forces scientists to reconsider the conditions of the early universe and the mechanisms that led to galaxy formation. Were the first stars far more massive and short-lived than expected, accelerating the cycle of star birth and death? Did dark matter play a more prominent role in organizing matter into galaxies than previously thought? These early galaxies, some appearing to be as massive as the Milky Way, are providing fertile ground for new theories and models to emerge. As the JWST continued to scan the skies near the edge of the observable universe, it detected more than just galaxies. It found regions dense with gas and dust, evidence of early star nurseries where stellar formation was underway at a furious rate. The telescope's infrared capabilities pierced through the obscuring clouds to reveal what had never before been seen: stars in the act of forming, embedded in the cosmic web that stretches across the universe. This cosmic web, theorized for decades and partially glimpsed before, became more vividly real under JWST's gaze. Vast filaments of matter connected ancient galaxies like glowing strands of silk, outlining the large-scale structure of the universe just as it was beginning to take shape. But perhaps most astonishing was the detection of gravitational lensing from massive structures near the cosmic edge. As light from background galaxies passed by clusters of mass in the foreground, it was bent and magnified, revealing otherwise invisible objects lurking in the dark. This gravitational lensing effect allowed JWST to look even deeper into the past, using nature's own telescope to peer into epochs that had remained hidden. Through this method, the telescope uncovered faint and distant proto-galaxies, clumps of matter just beginning to coalesce, offering a view of the very first stages of galactic assembly. The discovery of these objects is not merely a scientific triumph, it is a philosophical one. To look at the edge of the observable universe is to look at the limits of time and space as we understand them. The observable universe is not a boundary in the traditional sense. It does not mark the edge of all that exists, but it is the furthest distance from which light has had time to reach us since the beginning of the cosmos. Beyond this limit lies the unobservable, perhaps the unknowable regions of the universe that by the laws of physics we can never directly see. And yet, by approaching this horizon, JWST has enabled humanity to reconstruct the earliest chapters of the cosmic story, linking our present to a time when the very first light began to shine. These discoveries have also raised profound questions about the nature of the universe's expansion. The cosmological redshifts observed by JWST not only confirm the accelerating expansion of space, but also offer a new level of precision in measuring that acceleration. With more ancient galaxies plotted in the cosmic timeline, astronomers can now refine models of dark energy, the mysterious force driving this acceleration. If the rate of expansion varied more dramatically in the early universe than expected, it could indicate that dark energy behaves differently over time, a revolutionary concept that could redefine fundamental physics. Additionally, the mass and density of these early galaxies have implications for our understanding of dark matter. Standard models of cosmology rely on cold dark matter to explain how structures formed in the universe. But with galaxies appearing earlier and more massive than predicted, there may be a need to revise how dark matter clusters and influences normal matter. Does dark matter interact in more complex ways than we thought? Or is there an entirely new component to the cosmos, some hidden ingredient not yet considered? These questions now sit at the cutting edge of theoretical physics, energized by the revelations from JWST. Even the concept of time takes on new meaning when faced with these discoveries. The galaxies that JWST has captured are not just distant in space. They are distant in time. Their light has traveled for over 13 billion years to reach us, meaning we are witnessing them not as they are now, but as they were just a few 100 million years after the Big Bang. In this way, the telescope functions like a time machine, offering a glimpse into the ancient past that shaped everything we know today. Our solar system, our planet, and all life on Earth emerged long after these galaxies were born, making it all the more humbling to witness them through a metal eye orbiting far from our home. The detailed spectra gathered from these remote galaxies also shed light on their composition and activity. Using its instruments, JWST analyzed the chemical fingerprints embedded in the light and found signs of elements like carbon, oxygen, and nitrogen. These are the building blocks of life, and their presence so early in the universe suggests that the ingredients for complexity were available much sooner than expected. While these findings do not point directly to life, they raise intriguing possibilities about where and how life might have arisen in the vast stretches of cosmic time. If planetary systems formed early enough, and if they had access to essential elements, could the seeds of life have been sown in the universe's first billion years? Beyond the technical and theoretical implications, there's a more personal existential resonance in what JWST has revealed. To stand on the shoulders of such an instrument is to gain a vantage point that humanity has never had before. It is to see across the eons, to perceive the faint embers of the universe's first fires, and to understand that we are the product of a history that stretches far beyond our imagination. The light that the telescope captures is not just information. It is memory woven into the fabric of space-time, waiting to be decoded. Every galaxy, every flicker, every gravitational arc is a relic of time's unrelenting passage. And through JWST, we are finally able to touch that history with eyes wide open. This moment also marks the beginning of a new kind of exploration. Whereas previous telescopes have charted stars, mapped planets, and unveiled nebulae, JWST has crossed a threshold into the primordial unknown. It has extended our reach to the very brink of what is observable, teasing the idea that there is always more to discover, more to learn, more to wonder. The edge of the observable universe may not be the end of the story, but rather a new chapter. Just beyond that edge, reality continues, unseen, perhaps unfathomable, but undeniably there. What the telescope has accomplished is not just about distance or depth, but about connection. The galaxies it observed no longer exist in their original form. They have evolved, merged, or faded. But in capturing their ancient light, JWST has connected us to them in a profound way. Across the abyss of time, those galaxies are no longer isolated. They are part of our cosmic lineage, ancestors in the grand genealogy of the universe. Their story is our story. And with each new observation, that narrative grows richer, more intricate, more astonishing. As JWST continues its mission, scanning other corners of the early universe, the data it sends back will continue to challenge, inspire, and reshape our understanding. The edge it has reached is not a final destination, but a frontier, a boundary to be pushed, a mystery to be unraveled. What lies just beyond the observable universe remains hidden for now. But the telescope has already given us the tools, the insights, and the courage to pursue that next horizon. The universe, once silent and dark, now speaks to us through the ancient light captured by a telescope launched from Earth, whispering the secrets of beginnings we are only just beginning to understand. As the James Webb Space Telescope continues its voyage into the furthest reaches of space, it isn't merely collecting images. It's rewriting the foundational frameworks of how we understand the universe. What makes this moment so pivotal is not only the telescope's ability to detect objects at unprecedented distances, but also its capacity to study those objects in extraordinary detail. The precision of its infrared instruments allows astronomers to dissect the earliest light with a fidelity never before possible, pulling out subtle nuances in brightness, composition, structure, and temperature. In doing so, the telescope is not just capturing the edge of the observable universe, it's redefining what that edge actually is, giving us a deeper and more nuanced sense of the universe's first chapters. One of the major surprises that came with these latest observations was the abundance of ancient galaxies clustered in a relatively narrow stretch of space and time. Instead of finding a sparse and chaotic environment, JWST revealed a surprisingly dense field of galactic activity teeming with formation and interaction. This tightly packed environment implies that gravitational forces in the early universe were far more intense and efficient than previously imagined. Interactions between these young galaxies, such as mergers, collisions, and tidal distortions, appear to have been occurring much earlier than models had anticipated. These cosmic interactions would have accelerated the growth of galaxies, allowed black holes to form sooner, and influenced the distribution of matter on a vast scale. Further analysis of these densely populated regions has exposed traces of early black hole activity. Quasars, hyperluminous beacons, powered by supermassive black holes, are already present within a few 100 million years of the Big Bang. This is perplexing because standard models suggest that such massive black holes would need billions of years to accumulate enough material. Yet here they are, blazing from the depths of ancient time, forcing astronomers to reconsider the formation mechanisms of these gravitational titans. Could black holes have formed directly from collapsing gas clouds in the early universe, bypassing the slower star-seeding route? Or is there an unknown physics at play that enabled rapid black hole growth at a much earlier epoch? One particular discovery that has sparked intense discussion is the evidence of highly ionized gas surrounding some of the earliest galaxies. This indicates that these galaxies were key players in the epoch of reionization, the period in which the fog of neutral hydrogen that filled the universe after the Big Bang was gradually cleared away by the first luminous sources. Reionization marks a fundamental transformation in the cosmos. It was the moment the universe became transparent to light. JWST's detection of these ionized halos suggests that early galaxies were not passive or isolated phenomena. They were actively reshaping the intergalactic medium, sculpting the conditions of the cosmos for the generations of galaxies and stars to come. Another unprecedented insight came from the telescope's ability to study the temperatures and metallicity of early stellar populations. By analyzing the thermal emission and absorption features of these ancient galaxies, scientists found that some stars were significantly hotter and more luminous than typical stars we observe in the present-day universe. These are likely population 3 stars, theoretical first-generation stars composed almost entirely of hydrogen and helium, formed directly from the primordial elements of the Big Bang. While these stars had long been hypothesized, they had remained elusive due to their short lifespans and the challenges in observing them. JWST's observations provide the first indirect evidence that these stars not only existed but flourished, acting as cosmic engines that drove reionization and seeded heavier elements across the universe. Meanwhile, the telescope's ultra-sensitive instruments revealed subtle gravitational distortions caused by massive unseen objects lurking in the dark. These collusions, tiny warps in the structure of space-time, hint at the presence of dark matter clumps and filaments that, while invisible in themselves, influence the path of light from background sources. This has allowed researchers to create new, high-resolution maps of dark matter distribution at a time when the universe was less than 2% of its current age. These maps show an intricate lattice of mass that served as the scaffolding upon which ordinary matter could accumulate and form galaxies. This cosmic skeleton, once abstract and theoretical, has now taken shape through empirical observation, transforming our understanding of how the large-scale structure of the universe came into being. The telescope has also brought new clarity to cosmic voids, immense empty regions where matter is sparsely distributed. These voids aren't simply barren stretches of space. They are crucial to the dynamism of the universe's evolution. As JWST mapped the early cosmos, it discovered that voids already existed even in these ancient times, forming around denser areas of matter as gravity drew material together. The contrast between dense clusters and expanding voids shows that the cosmic web structure was taking form rapidly, guided by the competing forces of gravity and expansion. Understanding the behavior of these voids may offer insights into the mysterious interplay between dark matter and dark energy, and how that relationship shaped the fate of the universe. Another striking result came from JWST's investigation into cosmic time dilation. According to Einstein's theory of relativity, time appears to move slower in regions of high gravity and for objects moving away at relativistic speeds. With its ability to track the light curves of supernovae and variable stars at the limits of the observable universe, JWST has recorded clear evidence of this phenomenon. Supernova explosions, which normally last days or weeks in a local time frame, appear stretched over longer durations when viewed from Earth due to the enormous redshifts. This isn't just a theoretical prediction anymore. It's observable proof of how the fabric of space-time itself warps with distance and expansion, providing yet another affirmation of relativity on the largest possible scale. Delving into the chemical makeup of the earliest interstellar clouds, JWST found surprisingly high concentrations of dust and complex molecules. Dust is essential for the formation of stars and planets, acting as the seeds around which material condenses. The early presence of dust suggests that the cycle of starbirth and death was occurring at breakneck speeds, stars forming, evolving, and exploding in a matter of millions of years. Some of this dust contains polycyclic aromatic hydrocarbons, complex organic molecules that on Earth are associated with biological processes. Their appearance so early in the universe hints that the building blocks of life may have been distributed throughout space far earlier and more widely than ever considered. As JWST continued to look outward, it also looked inward, in a sense toward the fundamental constants that define physical laws. One area of interest has been whether constants like the fine structure constant, which governs electromagnetic interactions, have remained unchanged throughout cosmic history. By comparing the spectral lines of ancient light sources with modern analogs, astronomers are beginning to test the uniformity of these laws over time. So far, results suggest remarkable consistency, but even minute deviations could herald new physics, perhaps evidence of extra dimensions or alternative universes branching from our own. This push into the furthest realms of space has also enabled a new kind of astrophysical archaeology. By examining the fossil light of early galaxy clusters, JWST has unearthed galactic ancestors that later merged to form today's massive ellipticals and spirals. These protoclusters exhibit a diverse range of behaviors, some dominated by starburst activity, others by quiescent dust-shrouded cores. This diversity suggests that there was no single evolutionary path for galaxies, but rather a spectrum of outcomes shaped by local conditions, gravitational encounters, and environmental factors. Among the unexpected finds was a class of faint red galaxies that had somehow become dormant just a few 100 million years after forming. This quenching of star formation at such early epochs is deeply puzzling. For a galaxy to go silent so quickly implies extreme feedback mechanisms, perhaps from black hole winds or supernova explosions that expelled or heated the gas needed for new stars to form. These ancient red and dead galaxies defy the narrative of continuous growth and challenge astronomers to identify what physical processes could shut down star formation so efficiently and so early. On an even more speculative frontier, JWST's sharp vision has begun probing for signs of exotic phenomena predicted by advanced theories. One intriguing possibility is the detection of primordial black holes, hypothetical remnants of the early universe that formed not from collapsing stars, but from extreme density fluctuations shortly after the Big Bang. These objects, if they exist, could account for a portion of dark matter and serve as probes into the physics of the universe's first moments. Identifying their signatures, such as distinctive microlensing events, has become a priority as the telescope's data pours in. JWST has also initiated the first direct measurements of star formation rates at cosmic dawn. By observing nebulae in ionized regions, scientists can now calculate how rapidly stars were forming in the earliest galaxies. The numbers are astonishing. Some galaxies appear to be creating stars at rates 10 to 100 times higher than the Milky Way does today. This extreme efficiency points to a universe that was once a furnace of creation, rapidly churning out stars in a mad rush to structure itself before the light of its youth faded. All of this is just the beginning. The universe's edge is not a static perimeter. It's a shifting horizon, extending as the telescope pushes deeper, as methods improve, and as new generations of instruments come online. But what makes JWST's achievement singular is that it has cracked open a door that was until now sealed by time itself. Every photon it collects from the edge of the observable universe is a whisper from the ancient cosmos, encoded with stories that have waited eons to be heard. It is impossible to separate the technical from the profound when discussing what JWST has accomplished. The telescope, in its elegant silence, has shown us that the early universe was more complex, more vibrant, and more surprising than any theory had dared to predict. The darkness that once cloaked the cosmos in mystery is now being filled with knowledge, not in sweeping generalities, but in sharp, vivid empirical truths. The edge of the observable universe is no longer a line of ignorance. It is a frontier of wonder. What lies beyond remains out of reach, not because it is hidden by distance alone, but because the laws of physics define a limit to how far light can travel in the age of the universe. But in pushing to that boundary, JWST has not encountered silence or emptiness. It has discovered a symphony of creation, echoing from the first sparks of existence. Each observation is a verse in the great poem of the cosmos, a composition written in starlight and silence. The discoveries at the edge are a culmination of human aspiration, the urge to know, to see, to understand. It's a gesture that defines our species, not only to ask where we are in the universe, but to build instruments capable of finding out. And so, as JWST continues to look further, the edge expands, not in the physical sense, but in the conceptual, the philosophical. The universe is not static, and neither is our knowledge of it. With every new signal from the deep, the cosmos becomes a little more familiar, a little less abstract, and infinitely more alive. As the James Webb Space Telescope presses deeper into the void, its instruments now illuminate previously undetectable aspects of the cosmos's formative era. The subtle interplay between matter, energy, and time, long buried beneath the veil of deep space, is finally unfolding before our eyes. And among the most compelling revelations are not simply the galaxies themselves, but the delicate intergalactic environments in which they formed. These environments, rivers of hydrogen gas stretching across cosmic scales, act as invisible highways, channeling matter into galactic cores and fueling rapid growth. For the first time, astronomers can witness these filamentary structures in such early epochs with clarity, observing how they influence the placement, shape, and development of galaxies. This infrastructure of the universe, often referred to as the cosmic web, is no longer a theoretical framework derived from simulations. It's visible and dynamic, playing a crucial role in the galactic ecosystem of the early universe. In the earliest regions JWST has explored, the distribution of this cosmic web does not appear uniform. Instead, astronomers have found asymmetries and localized concentrations that challenge long-standing ideas about early cosmic homogeneity. These uneven distributions may have been the seeds from which the modern universe's structure eventually emerged, suggesting a more chaotic and varied cosmic landscape than previously imagined. The gravitational tug-of-war in these regions influenced which areas accumulated mass and which remained sparse. Some galaxies appear to have formed in the gravitational wells of dense nodes in this web, rapidly gathering gas and birthing stars at extreme rates. Others, positioned in less dense filaments or void edges, grew more slowly or remained isolated, evolving along different paths. In addition to structure, the timing and pacing of cosmic events have come under fresh scrutiny thanks to JWST's unprecedented temporal reach. New chronologies are emerging, ones that recalibrate our understanding of how quickly complex phenomena unfolded. Planet-forming disks, previously thought to emerge only after several 100 million years, are now being spotted around young stars in the first few 100 million years post-Big Bang. These disks, made of dust and ice, show telltale signs of planet formation. Gaps, rings, and temperature gradients, suggesting that planetary systems may have begun forming much earlier than any existing model anticipated. This revelation not only accelerates our planetary formation timeline, but also raises profound implications for the emergence of habitable environments in the early universe. Another unanticipated discovery has come in the form of high-velocity outflows, torrents of gas being ejected from early galaxies at speeds exceeding thousands of kilometers per second. These outflows, often driven by supernova explosions or active galactic nuclei, serve a dual role. They regulate star formation by clearing gas from galactic cores, and they enrich the intergalactic medium with heavier elements. JWST's sensitivity to subtle spectral shifts allows it to measure the composition and dynamics of these winds, revealing a surprisingly rich chemical signature. This material, expelled into the cosmos, forms the foundation for future generations of stars and planets. The dispersal patterns